We're now going to start our consideration of work and energy. So you probably already have an intuitive understanding of what energy is, but we're going to be looking at it a little more formally. So energy is related to the ability of a body to do work. Now, work has a special meaning in physics, and we'll be delving into this in more detail later, but work is related to the force applied to a body and the displacement of that body. Now, energy is a really useful concept, as in a closed system such as the universe, energy is always conserved. However, remember that not all systems are closed, so we need to be very careful when we apply energy conservation to check that our system is in fact a closed system. So we're going to be looking at different types of energy. So for example, we'll be looking at potential energy, which is a form of internal energy. So it's a stored energy, which can later be converted into kinetic energy, which is the energy of movement. Work is a method of transferring energy from one body to another body. So the SI units for energy are joules, and they have the symbol capital J. They're named after Sir James Prescott Joule, who was a physicist working in the 1800s who discovered the relationship between power, current, and resistance. Now, energy is a scalar quantity, so it doesn't have a direction, just a magnitude. So this means that some problems can be easier to solve using energy considerations than using force considerations, as when we consider force, we need to break the force into its different components and consider what's happening in every direction. With energy, we've only got the one component to consider, as it is a scalar, so it doesn't have different components in different directions. So as we said, kinetic energy is the energy associated with the movement of an object. So the kinetic energy of an object can be calculated using the formula that the kinetic energy K is equal to a half mv squared. In this formula, m is the mass in kilograms and v is the speed of the object in meters per second. So it doesn't have to be the velocity, because we don't need to know the direction that the object is moving in. We just need to know how fast it is. So let's just do a quick example. Let's calculate the kinetic energy of a car with a mass of 1,800 kilograms, which is traveling at 60 kilometers per hour. So we're going to need to substitute into our equation K is equal to a half mv squared. What's a little bit tricky here is that we've been given the speed in kilometers per hour rather than meters per second, the SI units. So our first step is to calculate the speed in meters per second. So the velocity is equal to 60 kilometers per hour, and then if we times this by 1,000 meters in a kilometer, and then times 1 over 60 times 60 hours divided by seconds, we end up with 16.67 meters per second. So now we can put that back into our original equation for K. So the kinetic energy K is equal to a half times the 1,800, which is the mass, times 16.67 squared. And this gives us 250,000, which we can write as 2.5 times 10 to the 5 joules.